Welcome back everyone. In the last lecture you have seen how to find out transfer function of a system experimentally. Today we go ahead and try to find out what are the different parameters related to a transfer function. In other words, what are the important terms that you can find from a transfer function that will help you tell more about the system. So, for that we will have to understand response of a system. So, actually there are different types of response of a system. In general, in the last class itself I had told you the word response means output in general. Now, the output of a system can also be divided into different parts. So, today we will be looking into that, at least one of those parts, and try to see how is that related to the transfer function of a system. So, if you remember, this was the differential equation that we are working with. Now, given a input to this differential equation, you will replace the right hand side of this differential equation with that particular input, and then you will try to solve it. You can use Laplace transform to solve this differential equation, and we had taken an example in one of the lectures before this, where you actually went ahead and found the step response of the system, where the input was a unit step signal. Now, as I already motivated that response can be divided into different parts, there is something called natural response of a system. Now, what is the meaning of natural response of a system? Natural response, physically it means the output of the system when input is 0. So, mathematically what would that mean? That means that you take this differential equation corresponding to the system that you are dealing with, you give ut equal to 0 on the right hand side, and you solve this differential equation, and you can see that this is nothing but the solution of a homogeneous ordinary differential equation. So, finding out the natural response of a system physically is equivalent to finding out the solution of homogeneous ordinary differential equation for the system. But do not you remember that we are talking about LTI systems, right? And we had already discussed in one of the lectures before this that to an LTI system, when you give 0 input, the output of the system is 0. Then what is there to analyze? There is nothing to analyze, right? Well, it turns out there is something to analyze. You see, when we were discussing all this, when I said that when you give input 0 to an LTI system, the output is 0, the primary assumption there was initial conditions are 0. What if there are initial conditions? Because think of it, I mean logically, I mean you do not even have to go through the mathematics, just think of it. You have a system which is an initial condition. For example, if you have a say RLC circuit, an initial condition can be like the capacitor voltage. Suppose the capacitor that you have connected to the circuit is already charged beforehand and you had connected it. So, it has an initial condition, it has an initial voltage. So, when you start the circuit, so what will happen basically? If you start the circuit, what should happen is that the voltage across the capacitor should start from the point whatever initial condition it had. Suppose you have the RLC circuit and you do not give any input to the system and you had connected the capacitor to the system, then what will happen? You can guess what can happen. The capacitor voltage somehow should dissipate and finally go to 0. Okay? If there is a way for the capacitor voltage to dissipate. If the circuit is open circuit, then you cannot do that, right? So, there must be a way for the current to flow out of the capacitor so that it dissipates the voltage across it. So, let us try to see what do you mean by natural response of a system in more details with the help of an RLC circuit as has been shown here. So, this is a series RLC circuit with R, L and C. Input here is voltage Vt, output is say the current flowing through the circuit. Okay. So, if you want to analyze the system, you will first have to find out the differential equation of this system. Remember, we are talking about natural response here, right. So, if we are talking about natural response, if I ask you, so the transfer function does not have any meaning in this case, because when you say natural response, the input itself is 0 and you have already considered the initial conditions to be 0, right. So, in that case, of course, so if you take, suppose Gs is equal to Ys by Us. So, if Us is 0, of course, Ys must be 0, right, whatever Gs it may have, whatever be the transfer function of the system. So, what we do is we find out the differential equation of the system. So, if you just write down the KVL equation, this will be the KVL equation. So, R into Y plus L di dt plus 1 by C integration I dt will be equal to the voltage applied here. Okay. Now, this equation, if you have to find out the natural response, to the right hand side you will put 0, right. And since see there is an integration here, and in the standard differential equation that we have seen had only differential equation, integration was not there. So, what we can do is we can differentiate both sides of this equation and then we will land up in a differential equation of this form. So, this will be the differential equation that governs the system when input is 0. So, if you find out the solution of this differential equation IT, then that is the natural response of the system. Again, remember, when I say natural response, I am talking about output of this system when the input is 0. So, when I make Vt equal to 0, what is the output of the system, and I have already declared that the output for this system is current IT. Okay. Now, similarly, let me take another system which is a spring mass damper system. Okay. So, a spring mass damper system can be of this form, where you have a mass and then it is connected with a spring whose spring constant is K, and then there is a damper whose damping coefficient is B, the mass is M. So, if you give a force here, the mass will move, right. That is what a spring mass damper system is. Now, let us try to see what will be the equation that will govern this and how will I find out the natural response for this system also. So, for that you will have to go for the free body diagram. So, let us find out the free body diagram for the mass. So, you see force is applied, and as a result of this the mass will move in this direction. Since the mass is moving towards this direction, there will be a reaction force of m A. A is nothing but d2 dt2 xx. So, this will be the reaction force from the mass. Now, since the mass is moving along this direction, the spring here will try to resist it, and the damper here will also try to resist it, and the spring and the damper will give a force of this amount. So, the damping force will be B dx dt, B into velocity and K into x. Now, if I write down the equation, force equation, the force equation will look something like this. Notice we are trying to find out the natural response. So, we will assume that the input is 0. So, in that case my equation turns out to be this. So, this is the equation, the differential equation that governs this spring mass damper system when the input is 0. This is the differential equation that governs this RLC circuit when the voltage input is 0 here. So, as a whole these are the two differential equations you have found, and notice that there is a similarity between the two differential equations. Both the differential equations are of the same type. Okay. So, mathematically if you think about it, think from a mathematician's point of view now, it is nothing but solving a differential equation, right, because both the differential equations are of the same type. So, instead of writing it separately, I can go ahead and write a simple differential equation of this form, where for the RLC circuit P1 is nothing but inductor, P2 is nothing but resistor value, P3 is nothing but 1 by C. and Z is I, whereas for the mass spring damper P1 is M, P2 is B, P3 is K and Z is X, the displacement. So, if I solve this equation and then whatever final solution I get, I will just have to take the physical interpretation. If I am an electrical engineer, maybe working in electrical circuits, the physical interpretation will be of an RLC circuit maybe in this example, and if you are a mechanical engineer with mass spring damper system, working with mass spring damper system, then the physical interpretation of the solution will be in terms of the mass spring damper system. So, let us look at this equation and try to simulate this equation. Okay. So, how are you going to simulate this equation? To simulate this equation, basically what do you mean by simulation? I will take some numerical values of P1, P2 and P3 and then I will try to find out ZT. Now, in order to find out ZT, I will have to solve this. Okay. Of course, you can analytically solve it with hand, you can calculate all the, you know how to solve differential equations, so you can solve that, but we are not going for that, we will try to simulate it. Now, it turns out to simulate it, it might be easier if I convert this equation, second order differential equation, this is a second order differential equation, right, there is a 2 here. So, the second order differential equation, I will convert this to a first order differential equation, and that can be done using very simple step, which is first let us define ZT as Z1, okay, and then I define another new variable Z2, which is nothing but the ddt of Z1. So, the actual Z is nothing but Z1 and Z2 is defined as the first derivative of Z1. Okay. Now, if that is the case, you see this equation can be rewritten now. This entire equation, this part can be written as ddt of Z2, because that is nothing but double derivative of Z1, which is nothing but double derivative of Z. ddt of Zt can be replaced by Z2 here, and Z here can be replaced by Z1. So, the entire equation, second order equation is being written in terms of Z1 and Z2 now, Z1 and Z2, and you can see that this has converted into a first order differential equation. So, if I write it down in this form, ddt of Z2, this will become minus P2 by P1 Z2 minus P3 by P1 Z1, this is the differential equation. So, this differential equation, second order differential equation has been converted into two differential equations, one is this and the other is this. So, as a whole, if I take both together, this is how the equation will look like. I am writing it in a matrix form. This type of converting a differential equation into first order differential equation will be very important for us when we go into the internal view of mathematical modeling, that we will deal with after some time. But for now, this is the differential equation. You can see these are two differential equations written in a matrix form. So, the first line here is nothing but Z1 dot is nothing but 0 times Z1 plus 1 times Z2. So, Z1 dot is Z2, this is this first equation, this equation, and here the second line of differential equation is Z2 dot, on the right hand side you have minus P3 by P1 Z1 minus P2 by P1 Z2, which is this equation. So, I have written both the equations. Solving this equation is equivalent to solving this second order differential equation, because solving this means you will have to find out ZT. Here if you solve this, you will first find out Z2 and then you will find out Z1. Although when we will do numerical simulations, we will not do it like that, we will solve this entire differential equation at one go, you will see soon, but you understand that solving this is equivalent to solving this. So, we have just converted the second order differential equation into a first order differential equation. Great. So, now let us try to simulate this. Okay. Let us try to simulate this first order differential equation. Now, I am putting the code here, I will explain the code and then I will go to MATLAB. Okay. So, here first thing, since I said I will simulate it, let us first write down the parameters. So, P1, P2, P3, P1, P2, P3, I have given some values, you can change it on your own also. Now, see, this is a first order differential equation. So, you will need initial conditions to solve it, and initial conditions will be nothing but Z1 0 and Z2 0. These are the initial conditions. So, I have to give the initial condition values. So, the initial conditions are 0 0 for the time being. Okay. So, and then for how much time do you want to simulate this differential equation for how much time do you want to see the simulation. So, from 0 to 10 we want to see the simulation. Okay. Now, once I have defined the variables, now let us look into the functions that have to be used to solve this differential equation. The first one, we are writing ODE fun equal to this. Of course, this name you can change, but I mean this is just the name of the differential equation. This is an easy way of writing. So, at the rate, first is the independent variable and second is the dependent variable. Here the independent variable is t and the dependent variable is z1 and z2. So, z is nothing but, so you remember z is being defined as z1 and z2. Okay. You do not have to explicitly define it. Again, in MATLAB when you use these percentages, these are comment. Okay. These are not getting, these lines are not getting executed. These are just comments to help the coder understand what is going on. Okay. So, of course, you can see in the comment itself we are defining the ODE system first. So, these variables we are defining, these are called state variables. I will come to what state variables are later, why the name state variable is there, we will deal with that later, but let us just look at the code, simple code at the rate t comma z. Then this is the important part. So, this is the part where I am writing down what is z dot and what is z2 dot, z1 dot and z2 dot. See, from here z1 dot is nothing but z2. So, see, I have written z2 here. Okay. So, in MATLAB, so since z is this, so z1 means z1 here. So, these are the syntax. So, in MATLAB when you write z2, it means the second element of the vector. The vector here is a 2 cross 1 vector. So, the first element is z1, the second element is z2. So, the second element z2. What about the second line? So, the second line is z2 dot. So, z2 dot is what? From here you can see z2 dot is nothing but minus p3 by p1 z1 minus p2 by p1 z2. That is what is being written, minus p3 by p1 z1 minus p2 by p1 z2. So, if you are dealing with some other differential equation, you can hopefully write it down. So, once you have defined the differential equation, now that we have defined the differential equation in MATLAB. So, now we will solve the differential equation. Now, to solve the differential equation, we use ODE 45. Syntax is first you write down the name of the differential equation. So, this was the name we gave to the differential equation. Then the amount of time for which you want to simulate solve the differential equation, which was this, and then the initial condition, which was these. See, the initial conditions has been written in vector form. So, in MATLAB when you write A semicolon B, this means in maths actually this. Okay. So, fine. After this it is just visualization. First we write down figure, so that the figure pops up. So, then we plot, even if you remove this it is fine. So, plot time, this is the x axis, and then we are just see, remember what is the output here. If you go back, see ZT we want to check, right, that was the output, right, ZT is the output in case of RLC circuit I, in case of mass spring X, this was the output and that is what we are trying to see, and Z is a vector of this form, right. So, we want to just Z1 is nothing but Z, right. So, we want to just visualize this. So, hence we are writing colon comma 1, colon comma 1 means suppose Z was a matrix like this. So, we are just taking up the first column. If we would have written this, then we are taking up the second column, okay. But we just want the first column because the first column itself is the Z1 vector. Okay. Then line width, I am just increasing the line width of the plot, so that it is we can easily see. Grid on is the grid will be seen, x level, x axis level, y level is the y axis level, title is the title of the plot. So, let us go ahead and simulate it and see what happens. Yeah, this is the code. So, see, initial conditions are 0 0 and these are the values of P1 P2. This is the same code, exact same code. Now, what do you expect? Think about it. You can pause your video here for some time and think about it. What do you expect? Initial conditions are 0, input is 0 because we are trying to solve the differential equation with inputs 0, right. That is what we are trying to solve. Input is 0, initial condition is 0. We know that this is an LTI system. So, output will be 0. Let us see. Let's simulate it. You see the output is 0, no change. Okay. Now let me just change the initial condition to say with a 0.1 here, and see the output, there is an output. Why is this output present? Although see, remember this is an LTI system, we are giving 0 input to it. So, we are expecting 0 output, but that will happen only if there are no initial conditions. If there are initial conditions, the initial conditions will take some time to maybe die down, or it might not die down also, it depends on the system. Okay. So, for now when we look at this, you see this is the response that we are getting. It is almost like a damped sinusoid. Can I change the initial condition? Yes, I can. I can even change the initial condition and make it 1000 here, say Z20 is 1000. You see, still the response looks similar. You keep on changing the initial condition, still the response will not see, the response changes. It's not that it doesn't change. You see, now it is starting from 10 to the power 5. Okay, so it's not that the response is not changing. We are only plotting Z1. Remember, we are only plotting Z1. So the response, it's not that the response is not changing, it's starting from 10 to the power 5. If I change it to 1, so it will start from 1. It is starting from 1, it is not visible because of the scaling. But the point that I am trying to make is that the structure of the response, or the you see, the response is always like a damped oscillation, right. Now let me just change the parameters. Okay. So initial condition I keep say 1000 or whatever you want to, I change the parameters, I make P2 say 5. You see the response has changed now. If I change the parameter further, let us make it 50, you see the response has changed now. So what I am trying to show you here is that the response is getting changed when I am making changes to the values of P1, P2 and all. I can even make this 10, let us see what it looks like. You see the response has changed. If I make it 2, you see the response has changed. So the response is depending upon the value of P1, P2 and P3. So it depends upon the initial condition, but the structure of the response, but the way the system is responding, sinusoidal, sometimes it is just shooting down, okay, I mean it is going to 0 directly. So how it is behaving depends upon the values of P1, P2, P3. So now let us try to understand why is this happening. So notice, if I go back to the system again, let us try to find out the transfer function of the system. Okay, now you will see that this is related to the transfer function actually. Okay, so let us go back to the transfer function of the system. So these are my RLC circuit and spring mass damper systems. So the transfer function of the system, you just do a Laplace transform on this, and again when we talk of transfer function, you have to first define what the input and output is. Remember, for the RLC circuit the output was Is and the input was Vs. So this is what we are trying to find out. For the spring mass damper, Xs by Fs, this is what we are trying to find out. Okay. So if you find out Is by Vs, this is the transfer function that you get. For Xs by Fs, this is the transfer function you get. Okay. So these are the transfer functions of the system. Look at the transfer function of the system. Important, look at something. Okay. If I take this equation, okay, and I just rewrite this equation, this will come out to be S square Lc plus, oh, I think that I have missed S here. Yes. So because the Laplace transform of integration of it is 1 by Sc. Okay. So 1 by Sc. So now if I just rewrite this equation, this is what it will become. So this becomes Src plus 1 whole into Is equal to Vs, and here this one becomes S square m plus Bs plus k whole Xs equal to Fs. See, both the transfer function looks different, although the differential equation had the same, I mean it looked similar, but the transfer function, you see here there is a Sc sitting over here, there is only one sitting over here. Although the denominator, look at the denominator in both the cases, the denominator in both the cases looks similar, only that the coefficients here is Rc, Lc, Rc and 1, here the coefficient is m, b and k. So from a mathematical person's perspective, it is basically a square plus bs, or I will not use b because I have already used b, maybe say ps square plus qs plus r. This is the denominator of both the transfer functions. Okay. Now, when I was changing the values of P1, P2, P3, notice what is changing. The denominators are changing, right? Because if you go back, let us go back. So, you see here P1 was L here, P2 was R here, P3 was 1 by C here, similarly M, B and K. So, when I am changing P1, P2, P3, I am basically changing the denominator polynomial, right. Now, it is the denominator polynomial that is actually governing how your system will behave, okay. And that is this brings us, basically it is the denominator polynomial's value coefficients that is governing how the system will behave, because when I change P1, P2, P3, I am changing the coefficients of the denominator polynomial. Of course, the numerator also will be important, that it is not just denominator, the numerator is also changing, right. So, both the numerator and the denominator polynomials are important, because when I change P1, P2, P3, I am changing the coefficients of the denominator denominator polynomial as well as the numerator polynomial. In other words, isn't it that when I am changing the values of P1, P2, P3, I am changing the roots of the denominator polynomial as well as the roots of the numerator polynomial, because the polynomial is changing, the roots are also changing, okay. This brings us to the idea of poles and zeros of a system. So, if you have a transfer function given to you, numerator by denominator, remember I had already given you a trailer of what poles are, in one of the lectures I had told you what poles are, and I told you that I will come back to it formally, I will define it later. So, this is where I am defining it. So, poles of a system are nothing but the roots of the denominator of the transfer function. If you look at the transfer function, you check the roots of the denominator, the roots of the denominator of the transfer function are called the poles of the system. In other words, the values of, again remember what are S? S are complex frequencies. So, if I change the value of S, in other words the values of the complex frequency that makes the denominator 0, if the denominator becomes 0, then the transfer function will become infinite, right. So, all those complex frequencies at which this transfer function becomes infinite are the poles of the system. What are zeros then? Zeros are the roots of the numerator of the transfer function, okay. And basically, in other words, all the complex numbers which when we plug in terms in place of S, that leads to the transfer function becoming 0 are the zeros of the system. That is how we define poles and zeros of a system. So, what I will do is, I want you all to find out general form of expressions for the poles and zeros of the system. I will help you with one of them, the easiest one, okay. So, remember the drone example that we took, we found out the transfer function to be 1 by s square. So, if I ask you what are the poles of this system, the poles of this system are the roots of the denominator, the denominator here is s square. So, the poles of the systems are 0 and 0, because you will solve s square equal to 0, there are 2 roots to it. Remember, do not forget to write down the other root, it is not like it has one pole which is at 0, do not do that. S square equal to 0 you are solving, so there are 2 poles, both the poles are at 0. It has a very important implication. So, if you forget about the multiplicity of the roots, it will become a problem. Where are the zeros? There are no zeros, because the denominator here is a constant. So, no zeros, okay. So, in this way, similar way, I want you, this is an exercise, I will not go into solving all this. So, I want you all to find out the general expressions of the poles and zeros of the systems. General expression means, in case of maybe RLC circuit, it will be in terms of R, L and C. When you change the value of R, L and C, the pole locations and the zero location changes. These poles and zero locations are what gives you that response. Remember, in one of the simulations we got a sinusoidal damping sinusoid. In one of the examples we got a peak and then it came down and it damped to 0, it went to 0. So, how will the response, how will be the natural response of the system will depend upon the pole and these pole locations, Okay. So, the natural response of the system are very important and it depends upon the pole locations. Okay. So, we will continue with this response, different types of response in the next lecture. Today we talked about natural response. Next we will see in natural response we never took input into consideration. In the next lecture we will take input into consideration as well and see how does the so what are the different types of responses that we have. Okay, and then we will go ahead and again come back to analysis of the system after defining the different types of responses. Thank you.